Hello and welcome to the Fireworks Sierra Nevada curriculum. My name is Mark Garrett. I'm with the UC Cooperative Extension in Mariposa County. The Fireworks is an educational program about the science of wildland fire designed for students in grades K to 12. And all these materials can be found online for free at frames.gov/fireworks/home. So this version of Fireworks focuses on selected ecological communities in the Sierra Nevada, which are forests dominated by conifers. These communities are often called lower and upper mixed conifer or lower and upper montane communities. To learn about some of the plants, animals, and fungi that live in these communities, see the essays in the Fireworks encyclopedias for elementary and elementary middle grades. Here's the Fireworks encyclopedia, and there are about 40 species you can choose from. And here's an example of what one looks like. The background on the species, as well as their fire adaptations. So like all Fireworks programs, the Sierra Nevada curriculum provides students with interactive hands-on activities to study wildland fire. It consists of 3 curricula and trunks of materials for educators. The 3 curricula are targeted at the elementary, middle, and high school levels and are great for adult learning too. So the trunks of materials, which you can find the link here, and it will give you a good idea of what's included in these. And at UC Cooperative Extension in Mariposa, we do have 1 trunk of materials. And if you're located in Merced, Mariposa, Madera, or Fresno counties, we can get that trunk for you if you need those materials. So the introduction contains information about program goals, curricula, featured ecological communities, and educational standards. So we'll just take a look at the introduction here. And it goes a bit over the why of fireworks, the goals, and I'm just going to read the local learning section, which has to do with the Sierra Nevada. So students learn best about ecology when it's close to home, when they can study the plants, animals, and fire regimes typical of local ecosystems. This version of Fireworks focuses on selected ecological communities in the Sierra Nevada forest dominated by conifers. These communities are often called lower and upper mixed conifer or lower and upper montane communities. These lower and upper montane mixed conifer forests have a long, intimate relationship with fire. The photo presentation created for Activity 1 in the elementary and middle school curricula shows many inhabitants of these communities and the different types of fire that occur in them. Lower montane forests grow just uphill from the grassy and shrubby foothill communities in the Sierra Nevada. Thus, they occur at relatively low elevations, not high in the mountains. Lower montane forests are dominated by oaks, ponderosa pine, sugar pine, white fir, Douglas fir, and incense cedar. Many of these forests, especially in historical times, were dominated by pines. They had an open structure with old large trees spaced far apart and few young trees. They had many kinds of grasses, wildflowers, and shrubs in the understory. A few of these old growth pine-dominated forests remain today. In the past, fires in this kind of forest tended to spread through the surface fuels. They rarely jumped into the tree crowns. Even when they did, they could not spread from crown to crown because most of these trees were spaced far apart. Because these forests are relatively dry, they typically burn frequently. Repeated fires keep the forest structure open. They favor grasses, wildflowers, and shrubs that can sprout easily after fire. And they provide habitat for mammals and birds that need large, old trees and an open understory. Upper montane forests occur at fairly high elevations, but not all the way up on mountainsides. These forests are usually dominated by Jeffrey pine, red fir, and lodgepole pine. There is a lot of overlap between lower and upper montane forests, so species from these communities often intermix. Because upper montane forests grow higher in the mountains, They are colder, receive more snow, and have a shorter growing season. Thus, historical fires generally burn less frequently than in lower montane communities, although there is considerable variability. In the past, fires in the upper montane forest tended to spread through the surface peels, but sometimes also jumped into the tree crowns. Fires killed trees in small patches, but most large trees survived. Mixed conifer forests in Sierra Nevada have experienced very few low-severity fires in the past century. Because of this, the forests tend to be very dense and have a lot of litter, logs, and ladder fuels. Ladder fuels are shrubs and young trees that increase in the absence of fire and enable fires burning on the forest floor to climb into the treetops. The forest canopy is fairly continuous, which means closed, and trees that grow well in shade are more common than they were historically. This is true throughout the mixed conifer forests, but especially so in lower montane communities. When fires burn through dense forests during hot, dry, windy conditions, they tend to burn in the tree crowns more often than they did when the forest structure was open. Crown fires kill more large trees than the frequent surface fires of the past. Nowadays, it is common to see large patches of stand replacing fires in forests that used to experience stand replacing fire in the small isolated patches. High in the mountains of the Sierra Nevada are the subalpine forests, dominated by lodgepole pine, western white pine, mountain hemlock, and whitebark pine. This curriculum does not cover the high elevation forest, but they are very important to the ecology of the Sierra Nevada and to the quality of life of its plants and wildlife, and to the human communities living in the watersheds below. So if we continue on with the introduction, there'll be a table, which is the summary of ecology and the fire story of some forest communities in the Sierra Nevada. And then you'll have the design and layout of lessons in the curriculum. So instructions for each activity also include a text box that lists subjects covered, the possible duration of the activity, and fireworks vocabulary, group size, and setting. The text box may also contain one or two icons, a red and white flame if the activity uses fire, and a brown box if the activity requires materials from the fireworks trunk. And then you'll have the links to the educational standards, which are shown here. But also, if you go back to the main homepage of fireworks and go under About Fireworks, the educational standards will be there. And the idea of the educational standards are that fireworks need not compete with core curriculum for classroom time. Instead, it can help teachers cover core concepts and improve student skills by using hands-on materials based on science from their own local area. So if we continue on with the Sierra Nevada curriculum, this table summarizes the content for each activity at each level. Read across the table to find similar activities for students at other levels. To access the entire curricula or individual activities, select the links in the table. So we're going to be looking at the middle school curriculum. And if you click on this link here, that will give you the download link for the entire curriculum, or you can download each lesson. So we're going to start in Unit 1, Introduction to Wildland Fire, visiting wildland fire in the Sierra Nevada. So for the description of this lesson, students view a narrated photo presentation that shows wildland fires and some of the plants and animals they are going to learn about. The slides and narrative are at the end of the lesson and on a PowerPoint. During the presentation, students record observations about fire behavior. Afterwards, they compare and contrast the kinds of fire they observed, and they also describe their feelings about wildland fire. The presentation's narrative is brief because this activity is meant to orient the students and let them express their feelings about fire, not to teach science content. So the goal increases students' understanding that wildland fire is a complicated process that has complicated effects and may generate complicated feelings. So some of the objectives are students can draw different kinds of fire behavior, they can compare and contrast different kinds of fire behavior, and they can describe their feelings about wildland fire. So if you click on the lesson plan link, it will have the same lesson overview there, along with the goals and objectives and the educational standards. And it'll have the text box, which shows you which subjects we're talking about, the duration, the group size, the setting, as well as some vocabulary words. And you don't see the flame or the box there, which is telling you it's not going to be using fire or the trunk of materials in this activity. And if we go down further, there'll be a bit of teacher background. I'll just go through this. So if you walk through a recently burned area, you might encounter some places where all the vegetation looks dead and other places that have a lot of green vegetation left. You might see deep holes in the ground where roots have burned away, and you might see patches of leaf litter that is just lightly scorched. Fire behavior and fire effects vary with topography, weather, and vegetation. As a result, some patterns are typical of certain kinds of landscapes and vegetation. For example, steep hillsides are more likely to support fast-moving fires than flatlands or most ravines, and forests with trees close together are more likely to support crown fires, fires that are spreading through the tree canopy, than forests where the trees are far apart. As an introduction to the study of wildland fire, this photo presentation highlights variation in the fire behavior and its relationship to specific plants and animals. This version of Fireworks focuses on ecological communities in the Sierra Nevada, forest dominated by conifers, which we've gone through previously. And it's telling you to go back through the introduction as well if you want more background on that ecological community. If you plan to teach the units on fire ecology 5 and 6, consider having your students adopt a plant, animal, or fungus now, so students have time to prepare, and you could spread their presentations out over several days instead of having them all at once. See activity 11, who live more fungus. Next, it will give you a list of the materials and preparation you're going to need, as well as the procedure. And procedure 1, explain to the students. They will view a short presentation that shows fire in the wildlands. In particular, they'll see different kinds of fire and different ecological communities. An ecological community includes all of the living things in an ecosystem: plants, animals, fungi, and microorganisms. An ecosystem includes the living things plus the non-living parts of the ecosystem, such as soil, water, and air. Ask for examples of community members in your school. Remember only living things. Ask for examples of non-living things in your school ecosystem. Ask which is more inclusive or bigger, community or ecosystem. Ecosystem is bigger because it includes the community and also non-living things. Number 2, explain that you will stop 4 times during the presentation and ask them to record something by sketching what they observe. After the presentation, you will ask them to compare and contrast different kinds of fire behavior and also describe their feelings about wildland fire. Number 3, give out copies of handout M01-1. Explain that you will let students know when you'd like them to use it to record observations. Next, show the presentation. You can use the narrative in the presentation notes or give your own narrative, but keep it brief. Welcome students to discuss and ask questions about what they see. Record the questions on a flip chart or other medium, but don't necessarily try to answer them during the presentation. Instead, explain that the class will seek the answers during this unit on wildland fire, and we'll come back to their questions in lesson 21, revisiting wildland fire. Be sure to save the students' questions if you plan to do lesson 21. Number 5, when you come to the 4 slides that show fire behavior and are cued to observe and sketch, slides 1, 8, 14, and 21, pause. Ask the students to look carefully at the flames in the photos. how long they are, and what parts of the plants they are burning, and record their observations by sketching the flames on their handout. They can also write a few words in the margin to describe their fire behavior. Give them a minute or more for each sketch. And number 6, after the presentation, have a brief discussion with the class about variety in fire behavior and also about their experiences with wildland fire and feelings about it. This discussion need not be long. It's a warm-up for the writing assignment. Next, if we go down to the assessment, you can ask the students to write on the back of the handout or on a clean sheet of paper a paragraph in which they compare the kinds of fire they observed, giving at least 2 examples of how the kinds of fire are the same. Also a paragraph in which they contrast the kinds of fire, giving at least 2 examples of how the kinds of fire are different. Also a list of 3 words or phrases that describe their feelings about wildland fire. Explain that people's feelings often differ with being right or wrong, without being right or wrong. So all of the feelings are valid. Also, since their feelings could change over time, they will have a chance to record their feelings again after they have learned more about fire. Okay, so now we're going to take a look at the slides and narrative for lesson 1, which are also included on here. Or if you go back to the lesson 1, you can find a link specific. So as you can see, this is a fire that's mostly burning on the surface and hasn't entered the crown of the trees. It does look like a fairly dense forest with a lot of younger trees. So give them a minute to observe and sketch it. And if we go down to slide 2, this is what the land looks like after that kind of fire, where it looks like most of the tree crowns have not been affected. There's still green needles up there. A lot of the surface fuels, the younger seedlings and saplings, have been killed. In slide 3, here's some plants that live in the forest after fire. A ponderosa pine tree that has survived many fires. And as you can see, there's the cat face or fire scar, which the tree has healed over. In slide number 4, you can see a Mariposa Lily, a wildflower that survives fire and then grows really well. And you could read more about these species in the Fireworks Encyclopedia. Slide number 5 shows a California black oak that sprouts after fire. So oaks can either resprout or drop their acorns and reseed. So they have a couple different ways of adapting to fire. So here are some animals that live in the forest after fire. A pileated woodpecker, which loves big old trees that have survived fires long ago. And here's a western gray squirrel that eats seeds of trees that have survived the fire. And here's another kind of fire in the Sierra Nevada. And this is the second one we'll be observing and sketching. And this looks much more intense, where we have crown fire. There's just fire everywhere. You can't really. So this is a very extreme fire behavior. So I'll have the students observe and sketch that. And this is what the land looks like after that kind of fire, which all the surface fields are mostly gone. And a lot of the tree crowns have been scorched, but you do still have some green trees in there as well. So there's some spacing there, which probably saved a lot of those trees. Or this is another example of what we just saw there, a more extreme example where all the trees have been killed and most of the surface fields are gone, and now we just have a vegetation conversion to where we're back to shrubs, and you only have a few trees that survived. In slide 11, here are some plants and animals that thrive after that kind of fire. A beetle with heat sensors, so it can find fires and lay its eggs in just burned trees. As well as a black-backed woodpecker, which arrives soon after the fire to eat the beetles. And deerbrush, whose seeds germinate after fire cracks open its hard seed coats. Slide 14. Here's another kind of fire in the Sierra Nevada. Observe and sketch it. And it says here, this is a mixture of two kinds of fire you've already observed. Many of those plants and animals can live here after fire. So you have the surface fire as well as crowning. Slide 15. Fire behavior and fire effects vary with topography, weather, and vegetation. Here are some examples of fire behavior, fires in the Sierra Nevada. Here's another example, more of a surface fire, slide 16. Slide 17, same sort of surface fuel fire, which looks like there's a bit of ladder fuels to get up into this tree crown, but it's not so dense here where it's going to be spreading to the other trees. In slide 18, we have more surface fire, but it looks not so intense. We don't see any trees getting crown fires or up into the canopies here. In slide 19, you'll see some torching of this tree. It might have been a dead tree already to help it get into the crown even quicker. But as you can see, there's spacing between these trees here, so it's not jumping from crown to crown. And slide 20. We have another similar to what we've been seeing, surface fire with going up the tree boles a bit, but not necessarily into the crowns because we don't have a lot of ladder fuels that enables that fire to do so. And slide 21, fires in our forest can burn for a long time after the flames have passed. They may burn in tree trunks, roots, or in the soil itself. Here's what a fire may look like after most of the flames have moved on. And this slide is the last one you'll be observing and sketching. So here's what the handout looks like for the fire drawings. Color each sketch to show which part of the forest is burning. For example, soil, surface plants, or tree tops. Add a few words to describe fire behavior if you wish. And here's A, B, C, D for each one of the 4 slides that we needed to observe and sketch. And also write one paragraph comparing the kinds of fire, giving at least 2 examples of how they are the same. One paragraph contrasting the kinds of fire behavior, giving at least 2 examples of how they are different. And last, 3 words or phrases that describe your feelings about wildland fire. So that is going to conclude lesson 1 of the Sierra Nevada curriculum, visiting wildland fire in the Sierra Nevada. Next, we're going to hop into where does heat go, the heat plume from a fire. Okay, so unit 2 is all about the physical science of wildland fire. And if we go a bit of the lesson overview, in this demonstration, students observe the heat from a burning candle on a single match so that they can describe the shape and size of a heat plume and explain how the energy from a fire is transferred. Since this is the first activity in fireworks to use actual fire, we suggest it as a demonstration so the class can go through and observe safety procedures together. So some of the goals will increase students' understanding of heat dispersal from fires and prepare students to safely conduct experiments with fire. And the objectives are that students can list 3 ways in which energy is transferred from a burning object, and students can describe the shape and size of a heat plume from a burning match, and they can list some safe practices for doing laboratory experiments with fire. And here are the online links for the PDFs and the lesson plan and the PowerPoints. So just like in all the other lesson plans, you'll have the overview, goals, and objectives with the text box talking about the subjects, the duration, the group size, the setting, and some vocabulary words. And we do have the flame here, which is going to be using active fire, as well as the trunk of materials. And here's the educational standards. And for the teacher background, most of the heat energy from a burning object usually disperses upward because the process of burning releases hot gases. The air at ground level is denser than that above because of gravity. So most of the hot, expanding gases of combustion tend to go upwards, the process in which warm gases and liquids generally move up and cool one moves down is called convection. The heat plume from a fire does not always go straight up, however. A gust of wind, which can be thought as a bubble of dense air, can push the hot gases sideways or even downward. There are two other ways to transfer energy from a fire: conduction, the movement of energy from one atom or molecule to another in a solid, or radiation, the movement of energy through space by particles or waves. The demonstration in this activity explores all three means of heat transfer from a single burning match. So some of the materials and preparation you're going to need is to choose your location. This demonstration can produce flames 10 to 15 centimeters long. Can you do this safely in your classroom and without setting off a smoke alarm? Can you take your students to a lab where it'll be safer? Do not try this demonstration outdoors because even the slightest wind will blow out a single match. And here's a list of some of the materials you're going to need that are included in the trunk of materials. And here's the procedure. Part 1, students demonstrate the three methods of heat transfer. So in this activity, the class will work together to make observations about heat transfer from fires. As background, you'll need to know three terms: convection, conduction, and radiation. We'll set up human demonstration to learn what they mean. Have students stand side by side in a long line, shoulder to shoulder, and explain and do conduction. If they were atoms within a solid object, like a metal, they would move heat energy by passing it from one atom to another, each atom absorbing some and passing some on. Pass the bag of candy to the first student, who takes a piece and passes it to the next, who does the same, all the way to the end of the line. And that's conduction. For radiation, get the candy bag back, if there's any left, of course. Now pretend you are a source of light and heat like the sun, radiating energy. You transfer that energy by sending out particles or waves through space. The energy travels until it contacts an atom or molecule, which then heats up. Throw a few pieces of candy directly to a few students. Radiation explains how you can get a sunburn from energy that travels through space. Amazingly, the molecules of your skin are the first ones that sunlight touches in its 93 million mile journey. And for convection, which is the expansion of a bubble of hot gases into the cooler gases surrounding it. Gravity holds Earth's atmosphere to the ground, so the air becomes thinner, less dense, as you go up in altitude. Since up has less resistance to expanding gases than sideways or down, hot air and the hot gases produced by combustion generally rise. Ask the class to imagine that their shoulder-to-shoulder line is vertical rather than horizontal. Pick 1 to 2 students to walk with you arm in arm from one end, the imaginary bottom of the heat plume, towards the other end, the imaginary top. Give a piece of candy to each student you pass. This means that your bubble of hot gases is losing heat as you go up, warming the surrounding air. If you run out of candy, stop. This means your bubble is the same temperature, or has the same amount of energy per volume as the air around you. And number 3, have students take their seats for the next steps. So in part 2 will be students will measure the shape of the heat plume. So firstly, we're going to explain the class will work with the teacher to safely measure the shape of a heat plume and learn how a fire can transfer heat through conduction, radiation, and convection. Number 2, go through the fireworks safety poster with the class, checking your demonstration setup to make sure all guidelines are met. And here's what the safety poster is going to look like. So when you do experiments with fire, number 1, wear cotton clothing, no synthetic pants, soccer shorts, etc., because those can melt with heat. And number 2, wear closed-toed shoes, no sandals or flip-flops. 3, tie back any loose sleeves. 4, tie back loose hair. 5, make sure fire extinguisher is close, make sure it is charged, know how to use it. And 6, make sure spray bottles are close and filled with water. And 7, wear safety goggles when burning. Number 8, never lean over a fire. Number 9, extinguish burned materials with water before putting them in the trash. Fire is not out if there is any smoke or heat coming from the fuels. And 10, if a fire starts on you, stop, drop, and roll. And use fire only if a responsible adult is working with you. And number 3, you're going to demonstrate how to safely light a match. Pull the match away from you, not toward you. Hold it level or tilt it slightly downward, not pointing directly downward. Drop into the ashtray or metal tray if it feels too hot. Always dispose of burned matches in the ashtray or on the metal tray. And these are materials that are going to be available in the trunk. And number 4, get a volunteer from the class to be the observer. Make sure he or she is dressed safely, following the poster guidelines. And 5, get another volunteer to be the measurer and another to be the data recorder. And 6, explain to the observer, your job is to find out how tall and wide the heat plume is from a burning match. You'll start by holding one hand about 40 centimeters to one side of the match. When the match is completely on fire, you'll bring your hand in closer until you can sense a change in temperature. The goal is to sense even a little warmth, not to see how close you can get without getting burned. We'll use as many matches as needed to get observations from 2 slides of the flame, above it and below it. When you make the below observation, don't put your hand directly under the burning match in case the tip breaks off and falls. Instead, hold your hand just a little to one side. Number 7, explain to the measurer. After each match is out, you'll measure the distance from its tip to the observer's hand in centimeters. And number 8, explain to the recorder. You'll mark the correct axis of the graph to show each measurement. And one of the downloads there was this graph here. So number 9, light the first match. As soon as it is completely on fire, obtain a side measurement and record it. After the match goes out, use the oven mitt to remove it from the clip. Put a fresh one in and get the opposite side measurement, and then a below measurement, then an above measurement. If you forget the oven mitt, you will quickly and painfully learn about conduction. Use as many matches as you need to get the 4 observation. Use the same observer for all 4 measurements. If you want to see variation from different observers, have another student or 2 repeat the observations, and then calculate an average for each dimension on the graph. And number 10, have the recorder connect the marks on the 4 axes, making a roughly oval shape. Refer back to the 3 ways in which heat is transferred in a fire: conduction, convection, and radiation. Discuss and explain the heat plume's strong tendency to move upward demonstrates convection. Radiation sends energy in every direction. The heat you feel from the sides and beneath the flame is due to radiation. Conduction of heat is occurring from the fire into the metal clip, which is why we're using the oven mitt. And number 12, you'll be cleaning up. Make sure all matches are out before you dispose of them. That is until there is no smoke and no heat being released. Use a metal trash can without a plastic liner. If in doubt, dump the materials in a bucket of water before putting them in the trash. And for the assessment, you're going to ask students to write and sketch answers to the following. Where did the heat go? Use heat transfer term to describe the movement of heat upward, sideways, downward, and into the metal pieces. Number 2, sketch a burning candle and show the shape of the heat plume. Label the diagram with words and arrows to show where convection and radiation are occurring. And 3, make a list of safety precautions that you should take when you get ready for school on days when fire experiments are scheduled. You can refer to the fireworks safety poster. And have students take the list home and post it in a place where they can refer to as they prepare for school. And lastly, here's the evaluation for teachers. Number 1, where did the heat go? You can use the vocabulary. The correct answer is most of the heat went upwards through convection, the tendency of hot gases and liquids to rise. And for radiation, a little heat went in every direction, the process in which energy travels through space in particles or waves until it hits a molecule, which it heats up. And some heat went into the metal clip by conduction, the transfer of heat from one particle to particle with a solid. An incorrect answer might look like student's description did not reflect the correct use of the vocabulary term or a general understanding of the concept. And number 2, for the burning candle diagram, you can see how radiation and convection are drawn. And an incorrect answer would be student does not have a correct drawing of the heat plume. They do not show that convection moves heat upward, and they do not show that radiation moves heat outward. And 3, for fire safety, at least 2 fire safety rules, for example, low flammability clothing like cotton, no loose or floppy clothing, closed-toed shoes, or hair ties. An incorrect answer would be fewer than 2 safety rules were listed. And that's going to conclude our lesson 2 activity. Where does heat go? The heat plume from a fire. Next, we'll be looking at lesson 3, what makes fires burn? The fire triangle, heat and fuel. Okay, for lesson 3, there are 2 online links, 2 PDFs that you can download. And for the lesson plan, for the overview in this activity and the next one, students learn about the concept of the fire triangle, then test it experimentally. And the goal to increase students' understanding of fire as a process of chemical change. And the objectives are that students can describe the chemical change that occurs in combustion, and they can explain why combustion is a chemical change. So here are the subjects: science, health, safety, writing, speaking, and listening. And it's about 1 to 2 half-hour sessions. And it's going to involve the whole class working in teams, about 4 students. And this is an indoor activity. And you could see it does use active fire, and it uses materials from the trunk. And here are some new vocabulary words. And here are the educational standards. For the teacher background, it says that this activity and the next one explore the chemistry and combustion as described by a conceptual model called the fire triangle. A fire cannot start without 3 things: fuel, oxygen, and a heat source. If a fire runs out of any of these things, it will stop. The 3 requirements for fire are conceptualized in the fire triangle. This is an appealing model because the geometric properties of the triangle are a good analog to the requirements for combustion. A triangle is very stable as long as all 3 legs are present. So stable, in fact, that it is used in the construction of buildings, furniture, and many other structures, and it collapses if one leg is removed. The triangle model is also appealing because it provides an easy way to introduce students to understanding a chemical change, the process of combustion. The three legs of the fire triangle actually represent the three inputs to the chemical equation for combustion, where H represents hydrogen atoms, O represents oxygen atoms, and C represents carbon atoms. Okay, so the equation above here does not give a specific formula for fuels because they could be any mixture of millions of compounds. The point is that all fuels contain a lot of carbon and hydrogen. They usually contain oxygen and many other kinds of atoms as well. For example, the equation for combustion of glucose with numbers of molecules balanced to show conservation of matter is this. The same equation represents cellular respiration, the process by which cells convert sugar into the energy that keeps living things, including us, alive. Furthermore, this equation is the reverse of the chemical formula for photosynthesis. Thus, the fire triangle can be used to introduce not only the basic chemistry, but also the basic principles of the biochemistry of life. William Cottrell's The Book of Fire, 2004, available from mountainpress.com, is a well-illustrated, easy-to-read description of the physical science of combustion and wildland fire. So handout M03-1, Why Does the Match Go Out?, describes an experiment to demonstrate that both heat and fuel are essential for fire, and the heat must be able to reach the fuel for combustion to occur. In the next activity, students use an experiment to investigate the importance of oxygen in combustion, and they may also learn the difference between chemical change and phase change. The materials in preparation: first you'll need to choose your location. If you burn in the classroom, be aware that this demonstration can produce flames 10 to 20 centimeters long. Can you do this safely in your classroom and without setting off a smoke alarm? Can you take your students to a lab where it'll be safe? Do not try to burn outdoors because even the slightest wind will blow out single matches and candles. So the day before doing this activity, remind students to follow the safety guidelines about clothing and hair when they get ready for school tomorrow. Get a package of hair bands to keep in your pocket so you can give them out as needed. Get 4 boxes of kitchen matches. The boxes need not be full. Draw the fire triangle on the board, labeling the sides. Make it big enough that you can add information next to and below it during the class discussion. Set up the teacher's lab bench with this equipment. And most of these materials are going to be available in the trunk, which is available from UC Mariposa location. Set up a lab bench or other safe space for each student team with the following equipment. And have a metal trash can or bucket without a plastic liner available. And make 1 copy per student of handout MO3-1, why does the match go out? So for the procedure, we're going to explain that the fire triangle is one way to understand what makes fires burn and what makes them go out. It is a model, something that helps us understand a process and make predictions about it. In the last activity, we made a physical model to demonstrate heat transfer, conduction, convection, and radiation. The fire triangle is a conceptual model. Let's briefly review and discuss the fire triangle. Then we'll test it experimentally. Next, we're going to ask students to name some fuels. List them on the board below the fuels label on the fire triangle. Don't limit the list to wildland fuels. For example, gasoline, birthday candles, and coal can be included. When the list is fairly long, Ask which fuels occur in wildland fires and underline them. Explain that all fuels are made up of many kinds of atoms all stuck together, especially carbon and hydrogen atoms. Inside the fire triangle and parallel to the fuels label, write these element names. You can add that fuels can contain dozens of other kinds of atoms, but carbon and hydrogen are the ones that are essential for combustion. And 3, point out that according to the list of fuels, burnable things surround us every day. Why aren't they on fire? There is not enough heat available to ignite them, would be the answer. Ask students to name some heat sources for fire and list them on the board next to the heat label again. Again, don't limit the list to ignition sources for wildland fire. For example, spark plugs and static electricity can be included. Underline the heat sources that can start wildland fires without human help, such as lightning and volcanic activity. And number 4, we're going to ask where the oxygen for fires comes from. Is it, of course, from air? Oxygen comprises about 21% of the air we breathe. Write air next to the oxygen label on the triangle. By the way, we only use about 20% of air's oxygen in a single breath. If we used all of it, cardiopulmonary respiration, CPR, wouldn't work. Number 5, do a safety briefing. In preparation for handling matches in these experiments, demonstrate a safe way to light the match, that is, hold it level or pointing slightly down, strike it away from you, and work over a non-combustible surface so you can drop it quickly but safely, even if it is still burning. Review the location of spray bottles and the fire extinguisher. And 6, we're going to give each student or team a copy of handout ML3-1 and tell them to follow the instructions on the handout. If they record multiple observations for A and B, you may ask them to calculate means and medians. As a class, discuss their answers. In regard to C, the downward pointing match probably burned almost completely. The fire went out mainly because it ran out of fuel. If a tiny stub of unburned wood remained in the alligator clip, it didn't burn because the clip absorbed much of the heat and limited the oxygen that could get to the fuel. The upward pointing match probably went out before it burned completely, so it could not have been limited by fuel. Students may guess that it was limited by oxygen. You can respond to this by asking if they have had any indication that the air around them is short of oxygen. Were they having trouble breathing? The explanation lies in the relationship between heat and fuel. Most of the heat was moving up away from the fuel, as they learned in activity M02. If any heat was going down, it was not sufficient to keep the wood burning. So number 7, below the fire triangle on the board, add the following line, which summarizes the chemical changes that occur during combustion. C, H, and O are abbreviations for the 3 kinds of atoms in this process. C and H atoms plus O2 plus a little heat equals carbon dioxide, CO2 plus water, H2O, plus lots of heat and light, or is greater. So we're going to show and explain the carbon and hydrogen atoms. C and H and fuels provide the first ingredient for combustion. O2 is the second ingredient, and heat is the third ingredient. Exactly the same kind of atoms are present in the products of combustion, carbon dioxide and water, but they have been recombined. It is that rearrangement of atoms that produces so much heat and light. Combustion is a chemical change, a rearrangement of atoms that changes substances from one kind to another. Most chemical changes are hard to reverse. For example, baking a cake causes chemical changes, and it's very hard to turn a cake back into its original ingredients. In combustion, fuels and pure oxygen are changed into carbon dioxide and water, and the change produces heat and light. Plants are the only thing on Earth that can easily reverse the combustion reaction. Photosynthesis combines carbon dioxide with water to form carbohydrates, comprised, as the name implies, mainly of carbon and hydrogen. So for the assessment, ask students to copy the fire triangle diagram and the chemical equation for combustion onto a piece of paper. On the paper, have them draw an arrow from each leg of the fire triangle to each ingredient in the chemical formula for combustion. Explain in writing why combustion is a chemical change. So for the evaluation, connect the fire triangle with the combustion equation. Correct answer would, the student drew 3 lines from the 3 legs of the fire triangle to the appropriate parts of the combustion triangle for oxygen, heat, and fuel. An incorrect answer would be, student did not draw the 3 lines correctly from the fire triangle to the appropriate parts of the combustion equation. And for 2 of the evaluation, combustion as chemical change, combustion is a chemical change because the atoms in the fuels and oxygen are broken apart and then recombined to form new substances, carbon dioxide and water. An incorrect answer would be, students did not communicate in writing an understanding of combustion as a chemical change. So handout M03-1, why does the match go out, is going to give us the steps we need to do for this experiment. So we need to organize your team, change the jobs if you repeat the experiment. On a team of 4, the observer should light the matches. The timer should measure the duration of burning in seconds. The measurer should measure the length of flames, and the recorder should record data. And step 1, place the metal tray on a heat-resistant surface. Set the support stand in the center of the metal tray. Attach the clamp to the stand, and attach the cross piece with the alligator clips to the clamp, so it forms a plus with the stand, like so. Clip a wooden match in each alligator clip. Attach one match, points straight up. Attach the other so the ignitable tip points straight down. And light a third match and use it to ignite the downward pointing match. Record your observations, A and B in the first column below. Always dispose of burned matches in the ashtray or on the metal tray. Step 4, use another match to ignite the upward pointing match. Record your observations, A and B in the second column below. And number 5, you may repeat the experiment to handle the alligator clips about conduction. And number 6, we'll answer question C for the downward pointing match. Then for the upward pointing match, which is use the fire triangle to explain why the match went out. And lastly, we'll need to clean up to make sure all burned materials and matches are out before you dispose of them. That is, there is no smoke and no heat being released. And also use a metal trash can without a plastic liner. If in doubt, dump them in a bucket of water before putting them in the trash. And that's going to conclude our lesson 3, what makes fires burn, the fire triangle, heat and fuel. Next, we're getting to lesson 4, what makes fires burn, the fire triangle, part 2, oxygen. Okay, so here's the lesson overview for lesson 4, what makes fires burn. In this activity, students learn more about the fire triangle and further test it experimentally. We described 2 options for doing the experiment. Option 1 using vinegar and baking soda, and option 2 using dry ice. And the lesson goal will increase students' understanding of combustion and the fire triangle model. And students can use the fire triangle to explain why various techniques work to stop fires. And here are the educational standards. And the text box goes through the subjects and the duration, which is about a half-hour session. The same group size, the whole class with groups of 4. Indoor setting, and it does include the flame, which uses active fire, and shows the box, which uses materials from the trunk of materials. And here are some new vocabulary words. So for the teacher background, initial background is in the previous activity, lesson 3, here is more. So the two options for experiments in this activity for M04-1 and M04-2 demonstrate that oxygen is required for fire. Both options use carbon dioxide gas. In option 1, the gas is produced by combining baking soda and vinegar. If you use this option, you can explore the chemical reactions between baking soda and vinegar. In option 2, the gas is produced from dry ice. If you use this option, you can explore the difference between phase change and chemical change. So about carbon dioxide gas, carbon dioxide is one of the components of air. It is heavier than oxygen, as you can see from this calculation of the molecule weights of the two compounds, where the carbon element is about 12 grams and oxygen is about 16 grams. And then it gives you the weights of carbon dioxide and oxygen. Thus, if carbon dioxide and oxygen are placed together in a container with no turbulence, the carbon dioxide will sink to the bottom and the oxygen will rise to the top. So for the option 1 background, these two equations describe the chemical changes that produce carbon dioxide from vinegar and baking soda. So vinegar and baking soda creates carbonic acid, and sodium acetate. Sodium acetate is the goo at the bottom of the container. Carbonic acid looks like water. The carbonic acid immediately breaks down into carbon dioxide, gas, and water. So for the option 2 background, when a substance changes from one phase, a solid, liquid, gas, to another, it undergoes a phase change. This is the difference from a chemical change. As described in the previous activity, in a chemical change, the molecules and the ingredients are broken into their component atoms, and the atoms are recombined to form new molecules. The change cannot be reversed easily. In a phase change, the atoms and the ingredients are not recombined, and the change can be reversed fairly easily. When you use dry ice for this experiment, you convert frozen carbon dioxide from the solid phase at a temperature of minus 78.5 degrees C or lower into a gaseous phase. Note that carbon dioxide does not form a liquid at Earth's atmospheric pressure, so it goes directly from the solid phase into the gas phase, hence the term dry ice. We say that dry ice sublimes, and the process is called sublimation. So for option 1, the experiment using vinegar and baking soda, some of the materials and prep you're going to need. First, you're going to choose your location. You'll be burning individual votive candles. Can you do this safely in your classroom and without setting off a smoke alarm? And can you take your students to a lab where it'll be safe? Do not try to burn outdoors because even the slightest wind will blow out the candles. So the day before doing this activity, remind students to follow the safety guidelines about clothing and hair when they get ready for school tomorrow. Get a package of hair bands to keep them in your pockets so you can get them out as needed. Get 4 boxes of wooden kitchen matches. The boxes need not be full. Get 1 box of long fireplace matches. Set up the teacher's lab bench with this equipment, the fire extinguisher fully charged and 2 spray bottles filled with water. Set up a lab bench or other safe space for each student team using the following equipment, which can be obtained through the trunk of materials. If possible, have a metal trash can without a plastic liner available, and print handout M04-1 for each student. So for the procedure I'm going to explain in this last activity, we saw that both fuel and heat are essential for fire to occur, but we didn't really look at the role of oxygen. That's the we'll explore in this experiment. And then review the oxygen part of the fire triangle. It comprises about 21% of the air we breathe, and we use only about 20% of the oxygen in a single breath. If we use it all in breathing, we couldn't use CPR to help a person who is not breathing. And as a review, ask students to describe the nature of a chemical change, a rearrangement of atoms that changes substances from one kind to another, producing a different kind of molecule. And 4, you will combine vinegar and baking soda in a chemical reaction that produces carbon dioxide. When vinegar and baking soda are combined, they produce carbonic acid and sodium acetate. The carbonic acid breaks down into carbon dioxide and water. You may want to share the chemistry below. And sodium acetate is the goo at the bottom of the container. Carbonic acid looks like water. The carbonic acid immediately breaks down into carbon dioxide gas and water. And 5, do a safety checkup with students using the fireworks safety poster that we've explored before. And 6, give each student a team a copy of handout M04-1. Have students go over the instructions, answer questions, then give out materials and have them conduct the experiment. After students have finished, discuss the responses to A through D in the table on the handout. Soon after vinegar has been added to the baking soda in the container, they should find it impossible to light the candle. Carbon dioxide has filled the bottom of the container. It is heavier than oxygen, so it doesn't rise and mix with the surrounding air. Instead, it crowds the oxygen out. Without oxygen, the candle won't burn. 8, now ask students to apply what they have learned. Ask them to name some techniques for putting fires out. List these on the board. Select one of them. And the discussion gets students to use concepts from the fire triangle to explain why the technique works. Then erase this technique from list, leaving the rest for the assessment. So for the assessment, select one of the techniques listed on the board for putting fires out. Write down the technique you've chosen. Use one or more components of the fire triangle and explain why the technique works. In your explanation, use at least one sentence and terms from the fire triangle. So for the evaluation, the student named the technique chosen. Explanation was logical and used one or more terms from the fire triangle. An incorrect answer would be the student did not name the technique. Explanation was illogical and did not reference the fire triangle. So for handout M04-1, for the baking soda and vinegar experiment, first, you're going to place one votive candle on a metal tray and light it. You will light matches from this candle. Next, you're going to place the other candle in a beaker or other container, as shown here. And then you're going to light the long fireplace match from the burning candle on the metal tray. Then use it to light the candle in the container. If either candle is hard to light, you may scrape some wax from around the wick. This step proves that the candle and the container can be lighted. Number 4, you're going to blow out the candle in the container. And then you're going to spoon 1 to 2 tablespoons of baking soda around the base of the candle, about enough to coat the bottom of the container. And be careful not to get the baking soda on the candle. Alternatively, you can add the baking soda to an empty container and then replace the candle. 6, you'll light the candle to make sure that the baking soda did not alter its ability to burn, then blow it out. 7, you're going to pour about 1/4 cups or 60 milliliters of vinegar into the baking soda around the candle. Do this slowly so the mixture doesn't foam so enthusiastically that it wets the candle wick. And 8, you're going to relight the fireplace match from the candle on the metal tray. Then use it to relight the candle in the container. 9, you're going to try different techniques for lighting the candle in the container. And 10, you're going to complete sentences to answer the questions below. And here's the answer key for this lesson. So describe what you observed when you mixed vinegar and baking soda. The mixture foamed, then a white substance accumulated at the bottom of the container, and it was covered by a clear liquid. For B, you're going to describe what you observed when you were lighting the candle in the container after vinegar was added. It was impossible to light unless the air in the room was turbulent or someone blew into the container. And for C, you're going to describe any techniques you used to light the candle in the container and explain how well each technique worked. This is a fun part of the experiment. Students may try moving more quickly. This won't work. They might try tipping the container sideways. This may work because you are pouring some of the carbon dioxide out. They also may try taking the candle out and pouring the carbon dioxide onto the lighted candle on the tray. That will probably extinguish the flame. And for D, you're going to use the fire triangle to explain your observations. And that is carbon dioxide is heavier than oxygen, so it stays in the container while the oxygen is pushed out. And without the oxygen, the candle cannot be lit. And for option 2, the experiment using dry ice, they're also going to give you a list of materials in preparation, which are similar, but there are some differences. So you still want to choose your location because you'll be burning votive candles. And if you could do it safely in the classroom without you setting off the smoke alarm, or if you have a lab to do it in, that would be great. And the day before the activity, make sure the students know about the safety guidelines for clothing and hair. And then you're going to make sure you have a package of hair bands with you so you can give them out as needed. You'll still need those 4 boxes of wooden kitchen matches. And get 1 box of long fireplace matches. And on the teacher's lab bench, you'll have that fire extinguisher fully charged, 2 spray bottles filled with water, as well as tongs for handling the dry ice. In the morning of the experiment, get 2 to 3 pounds of dry ice from a local supermarket. Store it in a cooler or freezer until class time, and find a hammer or something else for crushing the dry ice. And then set up the lab bench or other safe space for each student team using the following equipment, which can be obtained from the trunk of materials. And then if possible, have a metal trash can without a plastic liner available. And print handout M04-2 for each student or team. So the procedure for this lesson will be, in the last activity, we saw that both fuel and heat are essential for fire to occur, but we didn't really look at the role of oxygen. That's that we'll explore in this experiment. And then review the oxygen part of the fire triangle, which we've gone over before. And then ask students to describe the nature of the chemical change. And then explain as dry ice changes from the solid phase to the gas phase, the atoms are not rearranged and a different kind of molecule is not produced. The process of subliming dry ice is a phase change as opposed to a chemical change. Other familiar phase changes are the melting of regular ice into water and the evaporation of liquid water into water vapor. Phase changes are usually easy to reverse if you add or remove heat. For example, we can thaw ice, change from solid to liquid, and easily refreeze the liquid water back to ice again. In contrast, consider how hard it would be to unbake a cake. So for 5, do a safety checkup with students using the fireworks safety poster. And 6, more about safety. Explain you'll be using dry ice. This is frozen carbon dioxide. and it's very cold, minus 78.5 degrees C, or minus 109.3 degrees Fahrenheit. It's much colder than ice made from water because it is so cold it should never be handled without tongs or gloves or a thick oven mitt. If you leave dry ice in a container for a while, it will disappear because the solid carbon dioxide is subliming, going from the solid phase to the gas phase without a liquid phase in between. Gaseous carbon dioxide is invisible and comprises about 1% of air. For 7, you're going to give each student or team a copy of handout M04-2, have students go over the instructions, explain that you provide them with dry ice when they have finished the first 4 steps in the experiment, answer questions, then give out materials and have them conduct the experiment. When each team is ready for dry ice, use the tongs to place a few pieces in their candle container. The volume of about 2 to 3 ice cubes should do. And after the students have finished, discuss their responses to A through C in the table on the handout. Soon after the dry ice has been added to the container, they should feel the cold around the container and it should be impossible to light the candle inside. They may also observe fog in the container. This is not gaseous carbon dioxide. Remember, that is invisible. Instead, it is water vapor condensing out of the room's air because the gas in the container is so cold. Carbon dioxide has filled the bottom of the container. It is heavier than oxygen and is cold, so it is much denser than room temperature. So it doesn't rise and mix with the surrounding air. Instead, it crowds the oxygen out. Without oxygen, the candle won't burn. And number 9, now you're going to ask students to apply what they've learned. Ask them to name some techniques for putting fires out. List these on the board, select one of them, and a discussion gets students to use concepts from the fire triangle to explain why the technique works. Then erase the technique from the list, leaving the rest for the assessment. And 10, use the assessment and evaluation from option 1 above. So here are the steps for M04-2 using dry ice. Why does the candle go out? You're going to place the votive candle on the metal tray and light it. You will light the matches from this candle, just like in the previous one. Place the other candle in the beaker or the other container. Light the long fireplace match from the burning candle in the metal tray. Then use it to light the candle in the container. If either candle is hard to light, you may need to scrape some wax from around the wick. This step proves that the candle and container can be lighted. Then blow out the candle of the container. And then ask the teacher to place some pieces of dry ice next to the candle in the container. If you need to handle the dry ice, make sure you got an oven mitt on. And then you're going to relight the fireplace match from the candle on the metal tray, then use it to relight the candle in the container. You may repeat the experiment and use different techniques to light the candle in the container. And then you're going to have them answer the questions below. And here's the answer key for those questions. Describe what you observed when you were relighting the candle in the container. Well, the container was cold. It may have had fog inside. It was impossible to light the candle unless the air in the room was turbulent or someone blew into the container. And B, describe techniques you used to try to light the candle in the container. Explain how well each technique worked. This is a fun part of the experiment. Students may try moving more quickly. This won't work. They might try tipping the container sideways. This may work because you're pouring some of the carbon dioxide out. They may also try taking the candle out and pouring the carbon dioxide onto the lighted candle on the tray. That will probably extinguish the flame. And 4C, use the fire triangle to explain your observations. And just like the last lesson, these answers are the same. Carbon dioxide is heavier than oxygen, so it stays in the container while oxygen is pushed out. In addition, carbon dioxide gas, just as sublimed from dry ice, is very cold, so it's much denser than it would be at room temperature. Again, staying put in the container while oxygen is pushed out. Without oxygen, the candle cannot be lit. Students may think that it is too cold inside the container to light the candle, so the heat component of the fire triangle is missing. That is unlikely, but this experiment doesn't provide a good way to test this hypothesis. Perhaps they can come up with an experiment to do so. And that's going to conclude today's lessons for Unit 1, Introduction to Wildland Fire, and Unit 2, The Physical Science of Wildland Fire. Once again, my name is Mark Garrett. I'm a fire educator for the University of California Cooperative Extension in Mariposa County. My email is mdgarrett@ucanr.edu, and you can contact me for the trunk of materials if you would like to use those. And thank you very much for listening today. Appreciate it. And stay tuned, as next we will be looking into Unit 3, the Wildland Fire Environment. And then we will go on from there to Unit 4, Fire Effects on the Environment. Unit 5, Fire's Relationship with Organisms and Communities. Unit 6, Fire History and Succession. And lastly, Unit 7, People and Fire's Homeland.